So my dear student, today let us talk about non-autonomous dynamical system and their direction fields. Then we'll see some example also, further examples. So now first let us talk about non-autonomous system. So general non-autonomous system is given by equation of this type. So don't get confused. Sometimes I am using dy by dx, sometimes I am using dx by dt. Okay, so this is time variable, this is phase line or phase space. Okay, phase variable. All right, so let us see. It is very much similar to autonomous dynamical system. A general non-autonomous dynamical system, continuous dynamical system, means equation of this type, where in the right hand side there is no dependent variable x. Okay, so such type of differential equation or dynamical system we call general non-autonomous dynamical system. Let us see the characteristics of the direction field of such type of dynamical system. So yeah, for a given value of t, say suppose t is equal to t naught. Okay, for a given value of t, consider the line t is equal to t naught. This is parallel to this is x-axis and this is t-axis. Okay, so this is time axis and this is what? This is phase line space or phase axis. Okay, for a given time t is equal to t naught, let us consider the line. So this is t is equal to t naught, means this is the line parallel to this x-axis or phase line axis or phase space axis. Okay, phase line axis parallel to this one. Okay, so then what? Then tan theta is equal to what? Vt naught. At any point of this line, tan theta is equal to Vt naught. Fixed, it is constant. Then theta is equal to tan inverse Vt naught. That means what? So if you subtend, if you extend this line segment, to touch the time axis, then this angle is theta. This angle is theta. All right, so this angle is theta. So similarly at another point, okay, so the tangent line is there, and if you extend it to the time axis, the angle is same theta. Okay, that means these lines are all parallel. Okay, so for at every point on the line, okay, at every point on the line, the direction of the tangent vector is constant. Okay, all right, so they are all parallel. They are all parallel. Okay, on this line they are all parallel. So what is the conclusion? You draw any vertical line that is parallel to this x-axis. So at any point of the vertical line, if you just imagine about the tangent direction of the solution curve at that point, they are all parallel. Okay, so this is the characteristics of general non-autonomous dynamical system or differential equation. Okay, so what is the conclusion? At every point on the line t is equal to t naught, the direction of the tangent vectors is constant. So let us see some example then. Let us see some example of this one. Let me just click here. So here I am using dy by dx. Okay, so then the independent variable here is x and dependent variable is y, so we have to include only independent variable on the right hand side function. Okay, so suppose this is x square. Let us see x square. Let us see the function x square. X square, simple one that you can integrate it easily, and it also satisfies the existence and the uniqueness solution. Okay, of this differential equation. So this is the direction field, this is the direction field. All right, so think about vertical line here. So this is, in this example, this is x-axis and this is y-axis. Okay, so think about a vertical line here. So you can easily see that, verify that, so each line, the line segment or direction of the tangent vector at each point is parallel to at each point on the line. Okay, so here also, everywhere, and see, look at here, they are all parallel. Okay, look at here, they are all parallel. All right, so this is the characteristics of the general non-autonomous dynamical system, that direction field. Okay, let us now see the solution curve here. Okay, let us now see the solution curve at any point here. Suppose just click here, so this is the solution curve. Let us see here, it is solution curve, this is here. So you have lots of here solution curve, so you can do it yourself. I already mentioned you the website, so you can do it, practice it, drawing the you just compare the direction field of a autonomous system and non-autonomous system. Okay, you just compare the direction field of a non-autonomous and autonomous system. Okay, so then next, let us go to the example further. And next is, this is an example. So draw the direction field of the following system at a point. So this is a homework, this is homework. So I am giving you 5 point here. Okay, I am giving you 5 point here, 5 point. So you have to draw direction field of this system at this point. Okay, direction direction of the tangent vector of this system at this point. So this is homework, and this can be asked in examination also. Today light is very disturbing, so I could not make it my video in the earlier. So next, another example, let us see. So this is there will be less theory, and there will be lots of problem solving session in this chapter. Okay, so it is very interesting. Okay, I'll solve you some example, the similar example, you can solve it. Okay, so find the fixed points of the system. The next example, find the fixed point of the system, and this is the system. So what is this system? Is it autonomous or non-autonomous? Okay, you know it. All right, I have already explained. Draw the phase portrait, find the invariant set. Okay, so these are very important things in dynamical system, to find a fixed point, and then you draw the phase portrait, then invariant set. Okay, so these are very important things, concepts, notions. All right, so now let us see what is a fixed point. So fixed points are the solution, fixed points are solution of the equation dx by dt is equal to 0. That means x is equal to x into 2 minus x is equal to 0. So how many roots are there? X is equal to 0, x is equal to 2. All right, so 0 and 2 on the phase line, they are the fixed point of the given dynamical system. The behavior of the system depend upon the fixed point. Okay, nature of the fixed point. All right, so let us see. So fixed points are 0 and 2. Let us see. So on the left, let us first consider the fixed point x is equal to 0. Then think about some point just on the left of this fixed point, that means some negative number just near the 0, but it is on the left of the 0. Okay, that means some small negative number. Okay, in value, small negative number in value. So at the left of the fixed point, today I have finished my marker ink also. I could not go to market because of lockdown. So yeah, it is, font is very big, but it is not very clear. Okay, so anyway, I think you can read it. So x is equal to 0. Just think about some point on the left of x is equal to 0. Some small, some negative number is there. So then you put on the right hand side of the system, what do you get? So what do you get? Let us see. So negative, some negative number, some small, some negative number, then negative into negative is positive, so this part is positive. Okay, this part is positive. Negative number which is not more than 2, negative 2. So then this is negative, so negative into positive is negative, so dx by dt is negative. So from elementary calculus, what, x will be increasing. Okay, x will be increasing. All right, negative means x will be decreasing. All right, so x will be decreasing means what, so 0 is here on the left, here or here, so the value of the x will be decreasing, mean the motion or dynamics is in this direction. Okay, means phase point here under the dynamics, they are moving along this one, it is moving away from the fixed point. Okay, all right, so the behavior of the point just near the 0 on the left of the 0, they are not coming near to 0, they are moving away from 0. Okay, so that is the behavior. All right, next let us see at the right of the fixed point. At the right of the fixed point, that means some small positive number, let us see what is the behavior. So when you take some small positive number, small in the sense that is less than 2, then that is positive. 2 minus x will be positive. Okay, and x is positive, so it is positive into positive, it is a positive number. So let us see, then positive number, then it is dx by dt, in this case it is positive, therefore x is increasing. X is increasing. That means what, so 0 is here, if you take some small number here, then the behavior of the dynamics means the point is not coming toward the fixed point, it is moving away from the fixed point. Okay, so that is the thing. The fixed point nature, this such type of fixed point nature is called refailing fixed point, means near the fixed point, under the dynamics rule, they are moving away from the fixed point. Okay, they are not coming to the fixed point. So next let us consider the second fixed point, that is x is equal to 2 at the left of the fixed point. That means a point on the left of 2, very near to 2. Let us see, that means what, when x, the fixed point is 2, if you consider x which is less than 2, that means what, 2 minus x will be positive, and x is also positive. Okay, therefore it is positive. All right, so that is dx by dt is positive, means x is increasing. X is increasing. So that means what, let us see, this is 2, this is 2, just take points less than 2, then under the dynamics rule, the point is increasing, means it is coming toward 2. All right, so that is the thing, and there is clear difference between this fixed point and this fixed point. In case of this fixed point, near the fixed point, points are moving away from the fixed point. Okay, but here just consider one point very near to 2, but on the left of the 2, it's it is moving toward this fixed point 2. And next let us see some point on the right side. Let us see some point on the right. So at the right of the fixed point, x is equal to 2. At the right of the fixed point, x is equal to 2. Now what is dx by dt is equal to this one. So at the right means what, x is more than 2, then this quantity is negative, but this is positive. So positive into negative is negative, it is less than 0. So therefore x is decreasing. So therefore x is decreasing. So that means if you take points near 2 but on the right, means greater than 2, the point, and it is decreasing, means it is coming toward, the dynamics rule is that it is coming toward this fixed point. Okay, so there is a clear difference, the behavior of the fixed point 0 and the behavior of the fixed point 2. In the first case, points are moving away from the fixed point. In the second case, points are coming toward a fixed point. So such type of fixed point is called attractor. Okay, attracting fixed point, and this one we call it repelling fixed point. So such type of things we have discussed in the discrete dynamical system also. Okay, so whole phase line its behavior is now, you know, in the whole phase line, the points behavior is now we have, you know, determined completely. So dynamics we understand. Okay, so let us see the invariant set, how to find out the invariant set, you know. Then I told you any point here, you know, any point here, its movement, you know, it will never cross this 0 and come this side. Okay, in fact it is moving this way. So if you consider one point here, it will move this way. All right, that means this set starting from here 0 in excluding 0 up to minus infinity, any point, you know, in this set, so it will be here under the dynamics rule, the points movement will be all, on this part of the, you know, in the whole phase line. All right, similarly, you know, you think about any point here, any point here, any point here, excluding the fixed point 0 and 2. So any point here, so point here cannot cross this fixed point and come this side because it is coming this way. All right, so again point here, it, you know, it cannot cross this, you know, 2. It will be converging toward 2. Okay, after 2 it will not cross here. After 2 it is fixed point, means it will remain here forever, it will never reach here. That means what? Points on this open interval, so it will remain here only, it cannot move out of this set. Okay, so therefore it is called invariant set. Similarly 2 plus infinity is also an invariant set. So these are the invariant set. Okay, so what is the rule? You just consider one point in the invariant set, you know, so the movement or the orbit of that point will be, you know, confined in that, or invariant set. So that is why we call it invariant set. Invariant set is also very important concept, notion in dynamical system. Okay, so the invariant set, then the invariant sets are given by the, you know, this set. The invariant sets are minus infinity 0 and 0 2 and 2 infinity. They are all, you know, they are all open set, open interval in this case. Okay, so these are the thing I want to discuss with you today. You know, I am giving you little by little so that you can understand properly. So next lecture I will upload tomorrow. So thank you very much.